All right, last lecture in the chemical context of life. Welcome back. Um, in the chemical context of life, we're going to cover how to calculate moles and molarity so that we can understand acids, bases, buffers, and pH. See, solute concentration becomes an issue. We've been talking. If you recall, solute is the amount of stuff that's dissolved in a solvent. So solute concentration is amount of solute dissolved in unit solvent. Looking at an example from probably what you know. A packet of, I don't know, what's the yellow stuff? Yellow stuff's Splenda. A packet of Splenda in a cup of coffee. So the solute concentration would be 1 pack per cup. All right, easy enough. We can do that. If you were to make it twice as strong, have twice as much solute concentration in there, what do you have to do? 2 packs, 1 cup. 2 packs per cup. That's solute concentration. Let's say you wanted to make 2 cups. That has a solute concentration of 1 pack per cup. How many packets do you need? You need 2. So that you can make, so it's 2 cups and 2 packs. So 1 cup per 1 packet per cup. You've all done that. And that makes sense. The problem is, when we're dealing with, we can't just deal with weight. In these, 1 packet might be 1 gram. We need to deal with sorry about the pause there. My brain basically stopped. We need to deal with the differences in the number of molecules, not necessarily differences in the number of the mass. Because as you can figure, different molecules are going to have different molecular weights, which means that within 1 gram of salt, there's going to be way more molecules than in 1 gram of glucose, because salt, as a molecule, weighs several AMU less than glucose, which weighs, I think, 180 AMU. Salt, what is salt? It's 35 plus, I think salt is about 58 AMU, and glucose is 180 AMU. So you're going to have a lot more salt in the same weight as you have glucose in that same weight. So we need to figure out how to compare apples to apples, the number of molecules in solution of salt and the number of molecules in solution of sugar. And to solve that problem, we have this new measurement called the mole. So how do we figure out what a mole is? First off, back to salt, right? I'm glad I got the number right. You have to sum up the atomic masses of all the atoms in the molecule. The molecular formula of salt is NaCl. So 1 Na and 1 Cl. Well, we know the atomic mass here, the larger number, is about 23 for Na. And the atomic mass for chlorine is about 35 AMU. Remember those units. AMU for individual atomic mass. So 23 plus 35 is about 58, or if we could, add it up more precisely, 58.44 AMU, atomic mass units. All right, so that's step 1. Figure out the molecular mass. 58.44 AMU. Now we need to convert that to moles. 1 mole is simply the molecular mass of the molecule expressed in grams. So if 1 molecule of salt weighs 58.44 AMU, 1 mole of salt weighs 58.44 grams. Does that make sense? So the mole is just a mole is just the molecular mass expressed as grams. So if the molecular mass of sugar is 180 AMU, 1 mole of that sugar would weigh 180 grams. So we have 2 completely different masses for the same number of molecules. Then, to figure out molarity, all we do is dissolve that 1 mole of substance into 1 liter of water. So 1 mole of a substance into 1 liter of water, 1 mole of salt into 1 liter of water will be a 1 molar solution of salt. So that means that there are 58.44 grams per liter in a 1 molar solution of salt. There would be 180 grams per liter in a 1 molar solution of sugar. In a 0.5 molar solution of sugar, you would put 90 grams of sugar because it's half of a mole. To make a 2 molar solution, you would take 360 grams of sugar and put it into 1 liter of water because that's 2 moles of sugar in 1 liter. And that's how you determine those numbers. So 1 mole, and I want to stress this, 1 mole is equal to a certain number of molecules. A specific, I don't need you to memorize the number of molecules. I think it's 6.022 times 10 to the 23rd power molecules. But you don't need to know that. You need to know that 1 mole equals a set number of molecules, and it is equal to the atomic mass of that molecule expressed in grams. There we go. Why did I have to go through all of that? I had to go through all of that so you could understand molarity when we talk about pH, acids, bases, and buffers. And behold a lemon. As you know, if lemon juice gets in your eye, it hurts. I just did that this morning. I squeezed a lemon by accident, and it was pretty far away from me, and it always gets directly in your eye. I don't know if anybody, if you ever cut a lemon, it's not going to hit you anywhere but the eye. It's basically the spitting cobra of the fruit world. So water's got another property we didn't talk about in the last lecture, and that property is that at room temperature, water will spontaneously ionize. That means it spontaneously forms ions of hydrogen, so H+, which is also just a proton, and hydroxide ions, OH-. That water molecule literally splits itself. H2O becomes H+, and OH-. So it will automatically do that at room temperature. At room temperature, in absolutely pure water, you will always have 10 to the minus 7th molar hydrogen ions and 10 to the minus 7th molar hydroxide ions. That is a set property of water. If there are absolutely no other solutes present, you have likely never encountered water that is absolutely pure with no solutes dissolved in it. It is basically water that is freshly created in a lab in a perfectly clean, sterile tube in which hydrogen and oxygen were just bound together. It's unlikely you've ever experienced it. Honestly, I don't think you'd be able to taste the difference. But in pure water at room temperature, there's 10 to the minus 7th molar hydrogen and 10 to the minus 7th molar hydroxide in solution, and a whole bunch of obviously water molecules. Once you add solutes, the level of hydrogen or the level of hydroxide increases or decreases. When you dissolve a solute and it releases hydrogen ions, that is called an acid. When you dissolve a solute and it releases hydroxide ions or absorbs hydrogen ions, that's called a base. So you may have encountered these before. Orange juice, if you mix it with water, it's going to release a lot of hydrogen ions and make the solution acidic. Versus, say, bleach. If you were to pour bleach into water, it will absorb hydrogen ions and become more basic. Both of which are dangerous. Don't think that acids are dangerous and bases are fine. It's not the case. Both are dangerous and you'd have to take precautions when dealing with them. Oh, on the right there is apple cider vinegar. I don't know why people drink apple cider vinegar. My wife tried at one point to have me drink apple cider vinegar for health, I guess. I don't know. Anyways, she put it in the refrigerator, which is the wrong place for apple cider vinegar. So I went. I was outside. I cut the grass. I came in. I was so thirsty, and I came in and I saw this nice container of what I thought was apple juice, and I was like, "Oh, I'm gonna drink that." It took 3 gulps before I realized it was apple cider vinegar, and it hurt so bad. Don't do that to your loved ones. So we've got an acid is something that releases hydrogen ions. A base is something that absorbs hydrogen ions. If an acid or base gets completely dissociated, that is, the molecule completely breaks apart and releases a lot of hydrogen or releases a lot of hydroxide, it's termed a strong acid or a strong base, depending on what it releases. So this is a strong acid and base that completely breaks apart in water. A weak acid or weak base only partially breaks apart in water. That is, if you add water, some of the bonds between the base and the hydroxide or the hydrogen stay in place. So it doesn't get released. You release less hydrogen and less hydroxide into solution. So these are termed weak acids and bases. That hydrogen ion concentration will vary dramatically. The addition of a little bit of acid or a little bit of base will change the hydrogen ion content in a major way, anywhere from 1 molar to 0.000000000000000000001 molar, or 10 to the minus 14th molar. We don't want to deal with numbers like that. Nobody wants to deal with trying to figure out where the decimal is. I don't even know if I really said all the zeros right. So instead of using 10 to the minus 14th molar or 1 molar, we can make some sort of mathematical change, a mathematical transformation. So we're going to use what's known as the pH scale. Now, the pH scale is logarithmic. That means that for every number on the pH scale, from 1 to 14, you have a change in hydrogen ion concentration by 10 times. So the difference between 1, 2, and 3 is between 1 and 2, it's a 10 times difference. Between 2 and 3, it's a 10 times difference. That means that between 1 and 3, it's 100 times more or less hydrogen. So pH equals the negative log base 10 of the hydrogen ion concentration. The pH stands for, it's the French word for power, and I always forget what it is. I always think it's poisson, but then I remember that's from The Little Mermaid, and they were singing about fish. So P is the French word for power. Or I guess you could almost say it's the English word for power too. So because both start with P. So the power, P, of hydrogen, H. That's where you get pH. Equals negative log base 10 of the hydrogen ion concentration. If we do that, we're going to get some nice numbers, some numbers between 0 and usually about 14 that work really well. Up at the top of the scale, up near 0, you see battery acid, gastric fluid, so stomach acid. These are very, very acidic substances. So they have a very low value on the pH scale. If you have a large amount of acid, you have a low pH value. If you have a little bit of acid, you have a high pH value. So lemon juice is about 100 times less hydrogen in it than battery acid. Pure rain is at about 5.5. It's slightly acidic. That's because of the carbon dioxide dissolved in the atmosphere. So as it rains, it picks up carbon dioxide, which makes it into carbonic acid. That's where you get that's where you get acid rain. You'll notice at pH 7, it's freshly distilled water. There is 0 solutes in pH 7 water, this pH 7 solution of fresh distilled water. That means it's measuring that hold 10 to the minus 7 hydrogen ions and 10 to the minus 7 hydroxide ions. It is completely imbalanced. pH 7 is termed neutral. There is no difference between the amount of hydrogen and hydroxide present. And then as you go beyond 7, you enter into the basic area. Seawater, baking soda, all the way down to NaOH, household lye. If you want to get rid of, I don't know, a dead body, you put lye on it because it will take care of that problem. You'd need if you put it, I guess, in a bathtub with a really wide drain, it would work. But I'm not telling you how to kill and then get rid of a body. I'm just saying it's possible. Lye is pretty dangerous. So low pH is an acid, high pH is a base, pH 7 is neutral. pH is measuring the power of hydrogen. When we're looking at acids, we're talking about the amount of hydrogen ions present or the amount of hydroxide ions present. Remember, hydrogen ions can also be termed protons, free protons. We care about pH and about all this chemistry because they will impact biological systems. The shape of molecules can be changed by the amount of hydrogen or hydroxide present. And as you change the form, what else do you change? You change the function. That means that they, like here, you might have substrates and enzymes. Enzymes speed up reaction rates. They're not able to bind to each other, so reactions won't be able to occur. pH can stop ions and molecules from dissolving in water. Here we see glucose being dissolved by water. Well, suddenly, if glucose doesn't have the doesn't have free areas that are negatively charged, water won't be attracted to it, and it won't break the glucose apart. So pH can stop molecules from becoming dissolved or make them more easily dissolved. Most of your biological processes can only happen in a very, very small pH range, between 1 and 1.4. That is, you can have 10 times too many or 10 times too few hydrogen ions, but once you fall outside of that range, the shape of the molecules changes and your reactions stop happening, and that's bad. So you need to keep moving forward. You have to keep controlling your buffers. I'm sorry, not your buffers. That's what I'm about to get into. You got to keep controlling your pH. To minimize fluctuations in pH, you use buffers. Buffers are molecules that either take in or release hydrogen ions. They stabilize pH. They hold the hydrogen ion content in solution stable. The way these buffers work is they're going to either donate or accept hydrogen ions. Here we can see a weak acid and its conjugate base, its corresponding base. The way this equation works is if you've got too much of that acid, a high level of acid, the reaction starts to move in a downward slope toward the corresponding base. So the acid breaks down. So hold on. If you have too little hydrogen present, that weak acid breaks into its corresponding pieces, HCO3 and H+. So that releases hydrogen. If there is too much hydrogen present, now the corresponding base side of the equation goes up higher, too much hydrogen, and you flow down the other slope, creating more of that weak acid, H2CO3. This reaction goes back and forth until the levels stabilize at a set hydrogen ion concentration. Now, it's important to note that buffers do not neutralize some buffers do, but buffers do not in general neutralize a solution. Instead, buffers will stabilize solutions at a set pH. The buffers in your stomach, for instance, keep your stomach very acidic. They keep it at a low pH. But then once that chyme in your stomach moves onto your small intestine, your gallbladder, and you're going to have buffers released into your intestine to increase that pH to a much more, a higher pH that the intestine can tolerate. You've got different buffers in different parts of your bodies that bring the pH to different levels depending on the need in that area. Buffers do not necessarily neutralize solutions. They just stabilize pH by adding or removing hydrogen ions or hydroxide ions. So we talked about moles. Moles are just one way of measuring how much of how many molecules of a particular substance is present in an amount of weight, in an amount of mass. 1 mole measures the number of molecules, and it equals 6.022 times 10 to the 23rd molecules, whether it's sugar, salt, whatever. So that means that 1 molecule of substance can weigh a totally different. I'm sorry, 1 mole of a substance can weigh something totally different than the mole of another substance. We learned about moles so we can figure out how to measure solutes in solution, and we use the term molarity. 1 molar solution is equal to 1 mole of a substance dissolved in 1 liter of water. And we talked about that so we can understand how to figure out and quantify how acidic or basic solutions can be. An acid is a substance that, when dissolved, releases hydrogen ions. A base is, when dissolved, releases hydroxide ions. So we've got acids and bases, and we don't want to use these large and very, very small numbers to identify these. So instead, we put them through a mathematical transformation called pH. pH equals the negative log base 10 of the hydrogen ion concentration. So it's a logarithmic scale. Every one value on the pH scale is equal to 10 times the number of hydrogen ions or hydroxide ions. If you got a low number between 0 and 7, it's an acid. If you got a high number from 7 to 10, 7 to 14, it's a base. And if you are at pH 7, you are neutral. Now you can maintain pH at any of these numbers using a buffer, which are chemicals that either absorb or release hydrogen ions to stabilize the pH of the solution. That's a lot, but there you go. The basis of physical chemistry that we're going to need to understand the rest of the course. Moving forward, the next major topic we're going to cover is macromolecules. So we're going to take all of this stuff we know about water, all of this stuff we know about bonding, and start applying it to organic molecules like nucleic acids, carbohydrates, proteins, and fats. And we're going to see what those macromolecules do for your body and for the cell. That's coming up. I hope to see you soon.